we've seen everything what's on the blackboard. So, okay, so obviously we started from the Hamiltonian, and somebody asked me, it wasn't completely clear. So for me, J is always positive, because as you remember, we can play with J, the sign of J and delta, and by unitary transformations we can map these regimes onto each other, and as long as we are interested in the spectrum, it should matter. Okay, so this was the spin chain Hamiltonian, spin 1/2. We have spin 1/2 at each side, and we can rewrite this in this form, and then we recognize that it's nothing else but hardcore bosons jumping on the lattice. Okay. Many times it's useful to think in terms of particles, especially when we talk about scattering phases and stuff like that. Okay, so it looks like this. So you see that the chemical potential for these bosons seems to be 2H or something like that, right? So the main point is that the total magnetization in the z direction is commutes with the Hamiltonian. So I can go into a fixed magnetization sector, and this translates in this bosonic picture to a fixed particle number sector. Okay, and in this sense you can think about a fixed number of particles hopping on a lattice. Okay, so the wave function. Okay, so they have a maximalist neighbor interaction and they hop to the left or to the right. Okay, so the wave function, this is the famous beta ansatz, right? So the wave function we write, or the state we write in this form, the linear combination of states given in the position space. Okay, and so the coordinate representation of the wave function is a function of m coordinates. And the beta ansatz tells us that we should look for the solution in this form. Okay, so it's a linear combination of plane waves, but we don't know yet what the coefficients should be. Okay, but then we saw that in order for this to be a solution, an eigenfunction of the Hamiltonian, these coefficients should satisfy some constraints, or well, we found the functional form of the so-called two-particle phase shift. Okay, so the picture again in this particle picture, the idea behind this is that these particles scatter on each other, or if we interchange two particles, the wave function picks up a phase, and this is this phase shift. Okay. And even before this, we discussed the phase, what we expect for the phase diagram of this model. And now we've seen this at least 3 or 4 times. So if this is a magnetic field and this is an anisotropy parameter, then in this language, when J is always positive, this is the ferromagnetic XXX point, right? So here in this domain, we have, of course, we have a symmetric. Yes. This is a gap ferromagnet. Here, this is the ferromagnetic XXX. Okay. So isotropic Heisenberg with antiferromagnetic interaction, and this is a gap antiferromagnetically ordered phase. And between the two, we have a gapless phase. Well, I haven't really shown that yet, but we are just about to see that. And there is this H max magnetic field above which the spins align. So it's a ferromagnetically ordered state. We found that its value was J half and then delta minus 1 absolute value. Okay? And we haven't found yet the exact expression for this critical magnetic field. Okay, so here the spins ordered antiferromagnetically, total magnetization is 0, and we need a finite magnetic field in order to give some finite magnetization. And this is this critical magnetic field. Okay. So, are there any questions with this? Okay. And okay, still a reminder. So now we impose periodic boundary conditions, and as usual, this. Okay, I forgot to say, but here the wave function is parameterized by momenta, quasi-momenta. Okay? So these are not measurable quantities, these are just useful tools, okay, useful variables. The sum of them is the total momentum, it's measurable, but individually these particle quasi-momenta are not linear. Okay? So if we impose boundary conditions, for example, periodic boundary conditions, this quantizes the allowed set, allowed values of the momenta as usual, or quasi-momenta, and the equation that we get is a set of m coupled nonlinear equations. I didn't copy here the functional form of the phase shift, but you have it in your notes. So we have to solve these equations. So m equations, right? And they are coupled. So one trivial step which we can do is take the logarithm of these equations, then this product becomes a sum, and these quantum numbers appear. So what you can do is now you pick a set of quantum numbers, plug them in here, and then solve for the kj's. Okay, if you can find a solution, almost always you can only do it numerically, then you have your exact wave function. Okay. So now it turns out that the ground state is such in all phases that the quasi-momenta are real. Okay, so these equations have solutions where the kj quasi-momenta are complex, as we will see shortly. But if you suppose that they are real, then we can take the thermodynamic limit. So we can rewrite this equation, this fundamental equation, as an integral equation. So for this we need some density of solutions of this equation. Okay, some density of sometimes it's called density of roots or density of particles. This is what I wrote here. So this is how we turn this sum into an integral. Okay, so this was covered in Jean-Sébastien Paul's lectures much more carefully and in more detail. So this quantum number, you can think again about this as a function of the momentum, okay? And it's derivative with respect to k is just rho k. Okay? So this again, it was in Jean-Sébastien's lectures. It was worked out in detail. So one more step we needed is that, so this is an integral equation, but this is not equal to this, so it does not only depend on the rapidity, or sorry, the momentum difference, which you don't like. So we found new variables, the so-called rapidity variables, and then this equation has a chance to be translationally invariant, right? Okay, and the last step is taking the derivative with respect to lambda. And then we find this linear integral equation. This K is just the derivative of the phase shift over 2 pi. Okay? And as I said, the derivative of this f function becomes rho. So this is why it's an equation for rho, because it appears here as well as here. Okay. Good. And I don't know if I emphasized or not, but the ground state is given by this set of quantum numbers. I mentioned that this comes, you can think of this as given by some continuity argument that at delta 0, this system is just free hardcore bosons, or can be mapped to free fermions, hopping on the lattice. For that, we know that the ground state is a field Fermi C. So we fill each possible quantum, we pick each possible quantum number around 0 symmetrically, so that we have m of them. And these are our quantum numbers. Okay? And you can prove that in this case the solutions are real, and these are the ground states. So it's plural because we have in the different phases we found different, somehow we use a different description in each phase. Okay? Yeah. And so this integral equation, again, so this Q, the boundary of the integration, is set in principle by the magnetic field. Okay? So you can imagine that if we increase the magnetic field, this Q will increase or decrease. What do you think? Well, it should decrease, because if we reach H max, then we reach the aligned state. So let's say all spins down. So there are no particles, right? So the range, the Fermi C disappeared. Okay? And Fabian also mentioned this phase transition when we empty the Fermi C. So if we increase H, we decrease Q. Okay? But it's, I will give you some analytic expressions for this, but it's not easy to give this, to find this dependence exactly. And also to solve this integral equation analytically is not possible for a generic Q. But interestingly, one of the most interesting cases, the total magnetization 0 case, or we also call this half field, because in terms of the particles, we have n half particles. In this case, it turned out that Q takes the maximum allowed value, which is pi in this region and infinity in this region. You remember? And in this case, the equation really becomes translationally invariant, and you can just solve it by Fourier transforms, right? Because convolution becomes just ordinary multiplication after taking the Fourier transform, and we could find exactly analytical forms for rho. Okay, but this is the only case I have, basically, that we can do this. And you also you see again that if we used k's instead of lambdas, then we couldn't use Fourier transform to the Fourier transform trick. Okay. Okay, and then you can plot. I just did it because I want to see the ground state energy we had in each phase. Well, when I'm talking about ground states in phases, I'm not talking about this, right? Because here we know the ground state is just the ferromagnetic, our reference state. This. So here we had the result for the ground state energy in this regime and also in this regime, and we looked at this point as well, the XXX, antiferromagnetic XXX. But what happens if you want to plot the ground state energy? Looks something like this, more or less. Okay. So of course it's continuous when we cross the boundaries of these phases. Okay. And last time we started to perturb these equations, we wanted to excite the ground state. Okay, because I still haven't really proved that that this is a gapless phase, this is gap, and so on. Okay, so we are really interested in excitations, and also, if you remember, we wrote this equation in a shorthand notation. I wrote something like this. Maybe I realized that it's both conventional and easier to read if I put here this star sign, which stands for convolution. Okay? So the identity whose k convolved with rho gives this function. So this was one of our, this is the most important equation, but when we were looking at excitations, we also found, or yeah, we defined a function epsilon which satisfies this equation. Okay? And I'm not sure, I might have put number of 2 here instead of last time, I don't remember. Maybe I wrote 2c, but please correct it, so it's jc. And very importantly, this epsilon vanishes at the boundaries of the integration. Okay? So this is set by tuning the chemical potential mu. And this chemical potential, as I said, is basically twice as the magnetic field, which you can see from here. Well, you can say that actually this is just an integral equation I defined somehow. It's not completely clear, it's really the physical chemical potential. But you can, playing with these integral equations, one can prove that it's really the physical chemical potential. Okay, so, and the last thing where we left off, I think, was that we derived the change in energy if we add a particle or a hole, or we take away a particle from the sea. And we found that in general the energy change can be written like this, and the change in momentum was given by these expressions. Okay, so okay, I think this is where we finished. Okay. And one more thing which I want to mention is that we can compute in, this is still a bit formal because we haven't calculated these functions for the ground state, but in general we can also define the group velocity, which is, well, which is defined this way. But then this is nothing else but okay, so now prime means differentiation with respect to lambda. And then if you look at these formulas, you see that it's always given by epsilon prime lambda over the derivative of f. The derivative of f was rho. Okay, and this is v of lambda, and then of course the most interesting case is when we look at the boundary of the Fermi sea. So these are the low-lying excitations. This is what is most interesting. So then this becomes the density of, the velocity of speed of sound. Okay, so we have to take the derivative of epsilon in Q. And divide it by 2 pi rho in Q. And by this we can compute the velocity of sound. Okay, so in general, I repeat, these integral equations can be solved because they are linear very efficiently numerically, and you can play with the magnetic field or the chemical potential. So I guess one way to do it is you just set of chemical potential, then you solve this equation, you find a Q where this epsilon vanishes. So this epsilon will look like something like this. Q minus Q, so most probably. Okay, so it vanishes at some Q and minus Q, so this gives you a Q. Then you take this Q, you solve this equation, then you get rho, then you integrate rho and you find the magnetization. This is an indirect way, but parametrically you can then plot V, for example, as a function of magnetic field and so on. Okay. And again, epsilon the interpretation of epsilon was from here we see that this is the rest energy of the excitations when we take into account the backflow of the Fermi sea. Okay, and what we can do now, are there any questions? Because now, basically I just I ran quickly, I ran through what we saw last time. So this is a good point, good time for questions if you have any.
Maybe one question. Yeah. So H is the magnetic field, but as well the chemical potential, no?
Yeah.
So because this is sum over SZ is sum over N, so it's
yes.
So and then you plot the phase diagram H versus delta, so which I would call grand canonical for boson. If you want to fix the magnetization and you want to do the canonical, is there a direct way to plot the diagram? Or
First we did that actually. So and then it's simpler because then here this is delta 1. Here we have the ferromagnet. Now on this axis we plot as the total magnetization, and we have antiferromagnetic order, of course, only here where the total magnetization is 0. So somehow, see, this corresponds to this, and this corresponds to this. Okay. Okay, so let's look now at this equation, and maybe you also remember that I formally defined the resolvent operator R by this. Okay? So we can solve this equation formally by multiplying by I minus R. And what we find is minus J times C. Sorry, I forgot to say, but C was in the different regimes. It was either sinh eta when delta is minus cos eta, or sinus gamma when delta was minus cosine gamma. Okay, and I guess in our convention for the rapidities in the XXX point, it was just 1/2 if I remember correctly. I hope. But this you can check. So this is a general form. Okay, so I have to do this. And, well, here I act on the function 1, or sometimes I denote it by eta. Okay, so this is just the integral of this, the Dirac delta plus this Kappa, if you write it down in terms of Kappas. So here, I just deleted, but we have our fundamental equation which we can use. And so this is nothing else but 2pi rho. And here minus mu, well, this is the integral of these guys, so we can we can go back to the Fourier space, and then it's nothing else but the Fourier transform of the kernel taken at 0. Okay. And we last time we derived explicit expressions for R, rho, and the Fourier transforms. Okay. So this you can find in the notes, but you don't even need that, because what I want to say is that epsilon at plus or minus q must be 0. We haven't used that yet. Okay. So what does it tell us? It tells us that 1 minus mu is minus 2 pi j c rho in q. Okay. So now, if delta is smaller than minus 1, and I'm talking about we want to perturb the half field state. So Q took its maximal value. Wait a second. Yeah. Okay. Sorry. So let's look at this first. So here Q was infinite. So naturally the density of roots at infinity is 0. So we immediately see that the chemical potential is 0. But it's not really surprising. So here we have half filling with 0 magnetic field. And if we put just a small magnetic field, we immediately get some finite magnetization. Okay, but what happens in this other regime, the antiferromagnetically ordered regime? Well, now you look up R tilde, and you see that R tilde in 0 was 1/2. Okay, so we get that mu is minus 4 pi j c, and rho 0, I noted by rho naught this half field, so exact solution taken in pi. Okay. So why did I do this? Because this is just a critical chemical potential, if you wish, or magnetic field that is needed to turn on to give a finite magnetization. So this curve here, this HC, we found it exactly from this condition that epsilon that Q should vanish. Taking into account the factor of 2, this critical magnetic field, if I'm mistaken, it's 4 pi, 8 pi, sorry, j times, and actually C in this case was sinh eta, so let me okay, and now I have to plug in rho 0 in pi. So if you go back and check what it was, okay, we don't have too much time, so let me quickly write down the results. So it's 2j over pi sinh eta a m, and what is this m? Well, so k is the elliptic integral, and m is defined by this. Okay, so this was the only way to write in a closed form in terms of elliptic functions, if you remember. So if you plug in this Jacobian elliptic function, we plug in pi, then when we find this result. Okay? So m is basically equivalent to eta in this funny way. Okay? So now this is a function of eta, which means it's a function of delta. So we can plot this curve, which I did. in Mathematica, and I really found this shape. And actually, so very far from zero, these two lines become parallel. Okay, so we found exactly both the this magnetic field and both this lower or upper critical magnetic fields. Okay, so now let's see the excitations. Okay, so next. Excitations over the half of, let me write SZ0 ground state in the thermodynamic limit. Okay, this is what we are going to look at now. But this is what we started to look at last time with these formulas. We just didn't finish. So there's one subtlety, which is, so this mu that we found corresponds to this curve, right? So if you want to have magnetization 1/2, just a little bit below 1/2, then we jump on this curve. So here the chemical potential is just the negative of this. So it's not completely clear which one to use in these formulas. And it turns out that what you should, both for particles and holes, if we invoke particle-hole symmetry, so this formula gets a little bit, these formulas get modified, and this is the correct one. So if one does this computation a bit more carefully, a little bit more similar to what John Sebastian did, this is what you are going to find. Okay, and so these will be the energies of the excitations, of the particle or hole excitations. And the momenta are given here. So now what we need to do is to plug in our analytic solutions. So let's see. So delta. Let's see the antiferromagnetic regime first. Okay. Excitations. We want to see that this here near half filling we really have a gap phase. So just before that, a few words on this quantum number. So I just said that the ground state was given by this set of quantum numbers, and it turns out that if we shift everybody a little bit, let's see, this is some modified set of quantum numbers, the energy of this state is very close to the energy of this one. So the energy difference between these two goes as 1/n. So in the thermodynamic limit, it looks as if it was doubly degenerate. But in any finite system, these states are very close to each other, but they are not degenerate. So as delta goes to -infinity, you can think about these two states as the two linear, the symmetric and antisymmetric linear combinations of these male and anti-male states. Okay, and as delta goes to -infinity, then they really become degenerate, even in a finite system. Okay, and it turns out that if let's look at one-hole excitations. It turns out that if I take away one particle, which means I create a hole. Naively, you would say that you create a hole in this set of quantum numbers. but I will discuss this hopefully shortly. For each m, there is an allowed range of possible of the quantum numbers. They cannot take just any value. And it turns out if I take away one particle, I will have two more. So I will have n plus 1. I will have n plus 1 slots to put my quantum number. So now I have n minus 1 particles, but I have n plus 1 slots. So it means that actually I created two holes. Okay? And this corresponds to what we said in the first lecture, that if we imagine these excitations, that there are some defects in this nice nail order, then we saw that somehow because of the periodic boundary conditions, we needed to have two of these excitations. We couldn't have just one. So this, of course, Bethe is also about the periodic boundary conditions. So by this rule for the quantum numbers, we get back the same, that we need to put two. So we immediately have two holes. Okay. So if we want to look at just one hole, which is a hypothetical thing, just easier to write down. Let's see what we get. So delta P, again, it's minus 2 pi f lambda. So again, this f was the integral of the density of solution. And last time we wrote down this rho lambda explicitly. It was this. It was given in terms of this Jacobi elliptic functions. It wasn't that nice, but nevertheless, one can. Sorry, this is not correct. This is what I meant. So we integrate rho 0 up to lambda. So it turns out that you can perform this integral, and what you find is minus arc sine this function called Sn. Okay, I just give this for the sake of completeness. The message is that this can be written down analytically. Okay. Similarly, delta E, if I use this formula, I plug in everything, I find something okay, I was one step ahead of myself. So J. So let's see. So 2 pi J. This was a C sin eta, and this was my solution for the ground state rho. Correct now. And the most important, the more interesting thing is that, so now these are given in terms of lambda parametrically. But we want to write delta E, the energy of the excitation, as a function of its momentum. So we want to find a dispersion relation for this excitation. And it turns out that you can do it. And the result is just this. The one I started to write down. Just this. Okay. So there are some three factors. They depend on the anisotropy, so eta or m if you wish. And then this is this 1 minus sine squared. Is the functional dependence. So m runs between 0 and 1, so this is always real. Okay. So the minimum value that this energy can take is given when when delta p is pi half, right? Because then this is 1, and then all I have is 1 minus m square root. And this excitation always has this energy at least. So this is a gap excitation, okay? It cannot have arbitrarily small energy in the thermodynamic limit. So I can write that gap is j k m over pi sinh eta 1 minus m. And actually, I erase my critical magnetic field, but there, was it the same? Of course, it's there, still there. So it seems to be related to this critical magnetic field Hc over 2. Now I'm not really sure about this factor of 2. You can check. Okay, so this coincides with our expectations somehow. So this critical magnetic field is related to the gap nature of the excitations, and we can plot these. We will in a minute I will plot this dispersion relation. Before that, one more observation. Is that as delta goes to minus infinity, you can check how eta and m change, and you will find that the gap goes to j half delta absolute value, because that is negative now. And actually, this is really the naive energy of this excitation. Okay. With respect to the ground state. So you remember this naive picture of up and down spins was really true only for the easing limit, when delta is very negative, very big. But okay, we get back what we expected. Okay. So this is the energy, the dispersion relation for one hole, but in reality, as we discussed, we always have two holes. So we will have a sum of two excitations like this. Okay. So if you remember, this is we can superpose these excitations because the equation we solved for these delta A and delta P, they were just linearized equations around the ground. They were linear, so we can just add the energies of the excitation. Okay, so let's see now. Before I plot it, let's see this paramagnetic phase. So in this case, you can also write down. Actually, it's a bit easier. You don't have to deal with the elliptic functions. You can write down delta P, which turns out to be arctan sinh of pi lambda over 2 gamma. Okay, again gamma, cosine gamma, minus cosine gamma is delta. So this count, you can check it. I'm just using the formula I just erased, and I plug in the analytic solutions, the exact solutions for rho from the previous lecture, and I get this. Okay, so the energy is j pi over 2 sine gamma over gamma 1 over cos over 2 gamma. So again, I'm interested in the dispersion relation, and which is just which is just this. And and I can look at specifically at delta equals -1. This is the XXX antiferromagnet. Well, there these functions were really simple. You can do it. You can find delta and delta E and then express the energy in terms of the momentum. But you can also just take the gamma goes to 0 limit. In this case, it works of this expression. So we have E equals to J pi half cosine P, kind of this version. Okay, so let's plot these. So if you remember in John Sebastian Coe's lecture, he also solved for these excitations. He was looking for the elementary excitations over the ground state, and then he found this type 1, type 2 excitation for the Liebniger model. And this is the equivalent that for the Arcetri. Okay. So if you plot these one-hole excitations, they look like this. So this is pi half, this is momentum minus pi half, energy. Okay. So there's a periodicity, but the interesting thing is that it's periodic with the period pi instead of 2 pi. So these excitations live on the half the brilliant zone. So what I drew was, let's see, of course this is just a cartoon, you can plot it yourself. Okay, so of course this is the plot in these two cases. So you see that it's gapless, so here you have very, very small energy, and the slope of the curve gives you, again, the speed of sound, right? The velocity near low energies. So what is that? Around pi half, if you look at these expressions, you can read off immediately that the speed of sound is J, and it is very important, J pi half sine gamma over gamma. Just look at if you look at this. Okay, so this is an ingredient that Fabian Esser can use when he's doing the bosonization. It's one of the fundamental parameters that he can plug in. If you remember, his Hamiltonian had a V in front of it. So this is that V, if you wish. And we give this exactly, and then he can use the bosonization logic and for the low energy sector to compute many interesting things, correlation functions among others, which we cannot do at the moment, right? Okay, but what happens with these excitations? Well, these are gapped, so they look like something like this, I think. I'm not the best drawer. Okay, so here we have this. Yeah. Okay. But as I said, we were cheating a little bit because we always had two excitations. So, and also the experiments can only see these neutron scattering experiments can only see an even number of excitations. So what do they see? Well, you have to add two excitations of these, two excitations, so it gives a continuum. It looks like something like this. Let's see if I can draw this. Okay, so this is a continuum excitation. excitations, and now this is pi. It has the right trivialism. And minus pi. Okay. And if you've seen Takahashi's book, this picture is on the cover of the book. Actually, I wanted to give references. So one of the books, well, this is the person who worked out a lot of things about the XXZ model. Most importantly, the thermodynamics, which I hope I get to in the next hour. So this is one of the books. So let me mention before I forget. Another nice book is Sutherland's book, and both books. So they are not only about XXZ. You can find a lot of things about other integrable systems as well. Okay. So you see, it takes two excitations to. Let me see what I'm going to. It takes two excitations to change the total magnetization by one. Remember the number of particles, so there's a relation between the number of particles and SZ. So if you have two particles, you can change the magnetization by one. So this also tells us that these excitations are spin half. You can think of them as spin half particles. Okay. They will always come in pairs and give this continuous spectrum. And we have the speed of sound, we have the dispersion relation. So sometimes these excitations are called spin-ons. Okay. For the break, because we derived one important phenomenological parameter, the speed of sound. Let me just plot a few other quantities. Well, I can skip this. Okay, so one thing what one can again calculate explicitly, analytically, is that what happens in the gapless phase. Again, so here, what happens here if I turn on a small magnetic field? This is the gapless phase. So immediately we get some finite magnetization. And then we can calculate susceptibility, right? Which is the ratio of a small magnetic field and a small magnetization. Well, so it takes, what does it take? Well, you have to massage these integral equations. Now what you do is, because you change the magnetic field, you change the range of integration. So you have to take this into account, and you can work out the details. It's a little bit more complicated. It requires, to fix all factors, it requires to solve something which is called the Wiener-Hopf problem, so we don't have time for that. So let me tell you the result. So again, in this regime, if we define chi by 2sz over h, so this small sz is the total magnetization per site. Okay, S capital SZ over N. It looks like this. So this is when it's strictly smaller than 1. Okay? However, there is an interesting thing when delta equals -1, so when we are at the isotropic point, well, naively you would set gamma to 0 here, so it's still more or less okay because you find this. But of course, this also has corrections. This is for really small h and really small z. Okay, so h, I don't know, goes to 0. So it has corrections of the magnetic field, and in the isotropic case, these corrections, instead of being power laws, like in 1 over h, they have this form. There are these logarithms everywhere, and let me give you h0 because I find it really nice. It's a formula that has pi and e. Yes. So what this means is that as h goes to 0, of course this term becomes smaller and smaller. This is a correction. But if you plot pi as a function of h, near zero magnetic field, it has infinite slope. If you compute the derivative of this function, you find that it goes to infinity. So let me plot these things, and then I guess it's time for a short break. So let me first plot the magnetization per site as a function of h. Okay. So the maximum of this is 1/2. That's here. So you define these curves, and let's say this is the curve for delta -1. This is delta -1/2. Okay. And this is, let's say, delta -2. So, of course, here we need a finite magnetic field to induce some magnetization. So there is this value is exactly this HC, critical magnetic field. Okay? And of course, when we reach the maximum, so this is H max for that particular delta. Okay? So let's see. I did this for delta equals -2. Okay, because then we reach the maximum magnetization. And this the behavior here, this we can also derive. And so it has this square root nature. So what I said before, if we plot the susceptibility as a function of h, so these functions, and this is for xxx, then we know that at 0 it has a finite value 4 over j pi squared, but it has this infinite slope somehow. Okay? And this is because of this law. Okay, I guess it's time for a break. Are there any questions? So what time should we?
10 minutes.
10 minutes, okay.
Mm-hmm.
But I have some of these.